In this video, we are going to talk about two-factor ANOVA. Okay. Last time we talked about one-factor ANOVA, meaning that we were comparing the mean under one category. For example, we were comparing the weight of the pigs under the category diet, right? Under the diet category, there were different groups of pigs. We call levels, right? Group 1, group 2, group 3. But the category or the factor was only one, that was diet. Okay. So under the factor diet, we had 4 different levels. So sample 1, sample 2, sample 3, and sample 4. And we were comparing if those 4 different diets, okay, have the same impact on the weight or not, on the pig's weight or not. Okay. On this video, you will see there will be 2 factors, and under each factor there will be different levels. Okay, so you will be comparing the means under those 2 factors, also under the different levels under the factors. All right, so let's say this. In one way or one factor ANOVA, we study the effect of factors such as type of diet on the variable weights of pig. In this section, we study how the effect of 2 factors can be assessed using a single method. Instead of using a single factor ANOVA twice, this method not only saves time and money, but also useful to test the interactive effects of factors. In two-factor ANOVA, each factor has more than one levels. You know what the level means, right? Because under the diet we have diet 1, diet 2, diet 3, diet 4. They are the levels, right? The diet is a factor, and the title under one factor, the titles or the different groups under one factor are the levels. Okay. Usually for the non-parametric test of two-factor analysis, there are not reliable methods, and thus parametric methods are applied to the ranks of the data or expanded the Kruskal-Wallis test. We use different two-way ANOVA method if there are equal number of observations in each levels under each factors and for unequal number of observations. So if there are equal number of observations in each under each level, then we use one method, but if there are unequal number of observations, we use different method. Also, we will discuss the case where there is no replication, only one data in each block. Okay. So two-way ANOVA with equal replication, these are the steps. In each case, the number of data or the replication in each level of each factor are equal. Okay. Let us name the two factors A and B. Set A be the number of levels in factor A. So under the factor A, there are A levels, and under factor B, there are B levels. Under the uppercase B, there are lowercase b many levels, b many groups or samples, you would say. And N be the number of replicates in each of those levels. Okay. So let Xijl denote the ith element in ith level of factor A. So I'm sorry, let Xijl denote the lth element in the ith level of factor A and jth level of factor B. For example, x1, 2, 3 denotes the third element in the first level, third element in the first level of factor A, and second level of factor B. First level of factor A and second level of factor B, but this is the third element. Okay, so we will see an example clearly, but most of the time we do this type of problem by R. Okay, so we don't focus on by hand, because the calculation is so big, so we don't want to do these things by hand, but we want to go through the concept, right? How it works. Each combination of level of factor A with the level of factor B is called a cell. Thus, each cell has n replicates. Also, x bar ij denote the average of each cell. Also, we denote the average of all data from ith level of factor A by xi, and the average of all data from the jth level of factor B is x dot j. Okay, there is xi dot and this is x dot j for B. For A it is I and then dot. Thus total number of data is A times B times n. So how? Because see, there A has small a number of elements, right? And so B has small b number of elements, and there are how many replicates of each of them? So n many replicates, right? So it should be n here. This should be n. Okay. So the overall mean is sum of all those divided by the total number of n. So we always perform a two-way ANOVA using statistical software, as it is tedious to perform by hand. If you want to do by hand, we need the following quantities. So what we need is total sum of square. This is how we find it. Degrees of freedom is n minus 1, where n is the total of the total data. So cell sum of square, this is the formula you use. Within cell, this is the formula you use. Factor A sum of square, factor B sum of square with the degrees of freedom, and then you do A times B sum of square. This is for the interaction, we'll need that. Cell sum of square minus factor A sum of square minus B factor B sum of square, and the degrees of freedom here is that formula, and mean square of a factor is sum of square of the category over degrees of freedom of category. Then we calculate the test statistic, divide the ms of the category by the within cell of ms. This is what we have, right? ms of the factor, and the critical value is f alpha 1 df and dft. So this is how we do by hand. Okay, let's see this example. So two-way ANOVA. So the following data represents the plasma calcium concentration in milligram per 100 milliliter of blood of birds of both sexes. Okay, so here you see that one factor is the treatment type, no hormone and hormone treatment, and another factor is the gender, right? So under the no hormone treatment there are two gender levels, right? So what I would say is, I would say like this. This is the factor 1, right? Factor 1. So the first factor is the treatment type, so hormone, no hormone, and the second factor is the gender, so male and female. Under the no hormone there are two samples. Under the hormone treatment there are two samples as well. So alpha equals to 0.05. So what is the question? Test whether there is an effect of hormone treatment on the mean plasma calcium concentration, meaning the mean under the hormone and non-hormone treatment. Are the average plasma calcium concentration same under the hormone treatment and non-hormone treatment? That's the one question, right? Second question is test whether there is a difference on the mean plasma calcium concentration between male and female. So there are, this is male, this is also male, right? So is that the average plasma concentration on the male versus female, are they equal or different? That's the second thing that you want to do. And the third thing is test whether there is an interaction of sex and hormone treatment to the mean plasma calcium concentration. So what does that mean is basically, so is the average of the hormone and non-hormone treatment are or depend on the male and female or not? That's what you are going to test for the concentration. Okay, we will see this in examples as well. So this is by hand. So you find A equals to 2, meaning how many levels are under the hormone treatment? There are two, no hormone and hormone. So B is 2, meaning under the gender, how many levels are there, male and female? B is 2, right? And L is 5. What does that mean? L is 5 means how many data are there in each of those levels? 1, 2, 3, 4, 5, right? That's L is 5. So N is 20, means how many total number of data? That's the total number of data is 20, and you find out x bar is 21.825. So isn't that the overall mean? That's the overall mean. And x1 dot is the no hormone treated. So under the no hormone treated, so what is the average? x1 dot bar, that's what it is. And similarly find out x2 dot bar, and then x dot 1 bar is female, just for the female, find the average, and for another one is for the male. And x11 bar is first factor, first label, that is female, right? First factor, first label is female. So similarly you find out all those things and plug it into the formula, and then you decide. Okay, so this is the steps, these are the steps to do that. And then let's see the node. We'll see this example in R. Okay, let's see this node. So for concentration, the above method is fixed factor, meaning the factors are not chosen randomly. Sometimes if there are many factors and if you pick 2 factors randomly, in that case we use random factor method. And another node is, so basically what do you mean by fixed factor? Is there are just 2 factors and then you are just picking those 2 factors, right? Under the no hormone treatment and hormone treatment, there were just 2 factors, you pick those. And then so under male and female, there were just 2 factors, just 2 labels, and then you just pick those. There are just 2 labels, you pick those. But if there are like no hormone treatment and hormone treatment and another treatment and another treatment, so if you pick 2 randomly, that will be random factor. Okay, but here all those labels under the factors are fixed. That's why we call fixed factor ANOVA. Two-way ANOVA have some assumptions on the population as the one-way ANOVA. The data at each cells came at random from normally distributed population, and the variance is same in all the populations represented by the cells. This test is fairly robust if the population has minor deviation from normality, but if the p-value is close to the given alpha and if the population does not satisfy the assumptions, then we should not make a definitive decision from this method. Okay, and let us talk about the unequal replication. Okay, and without replication, if the cells have unequal number of data points, then the above procedure is not applicable. Unequal replication could be in rows or in columns or in both. There are 2 types in this case: proportional replication and disproportional replication. However, it is advised that you collect equal number of data in each cell. Usually we use statistical software capable of performing such ANOVA for such situations. Okay, it is advisable that a 2-factor experimental design have more than one data in each cell, but sometimes you may have only one datum for each combination of factors, that is n equals to 1. Only the difference will be the data will be of the form xij, where I denotes the level of factor A and j denotes the level of factor B. The procedure is similar to the one in above example, except n equals to 1, and we will not have summation 1 through n in the formula. So instead of 3 summations there in the formula before, we will have just 2 summations, because this will be just one data, right? So let's go over this. Before you perform a two-way ANOVA, you need to check the assumptions. Homogeneity of the variance, this is one of the important assumptions, and normality of the dependent variable, right? So normality of the data is also a very important assumption across each group, and no outliers. There should not be outliers. The test is robust for the mild violation of the normality. If the assumptions are not met, either you correct your data or use alternative statistical test. Also better to include them in the discussion. If there is an outlier, you can replace it with less extreme value or transfer the data into other form, okay, in case of the outlier. Or proceed under the assumption that the outliers will not affect the analysis, okay. Normality can be checked by using Shapiro-Wilk test. We will see in the R file. If not normally distributed, you can transfer the data to or use non-parametric test. ANOVA is robust for a small violation of the normality. If the data is severely non-homogeneous, there is a chance of type 1 error. Homogeneity can be tested using several statistical methods. We will see that in R. If you do not have homogeneity, you can make it homogeneous by transferring the data into other form or declare that your data do not meet the assumption and stop there. Okay, so this is the homework problem we will be doing. Okay, so before that I will show you how to do an example in R. Okay, and I will try to do this example in R as well. So basically I will go through two examples. All right, let us see how to do this two-way ANOVA or two-factor ANOVA in R. So make sure that when you are doing the two-way ANOVA in R, you need to have a separate column for each factor. Okay, so do you remember that when we were doing the one-way ANOVA we had a point 1, point 2, point 3 and point 4, and then there were so these are the data, right? So the factor was pound. Okay, the factor was the pound and the data was the pH level. Under the single factor pound we had 4 levels in the example we did previously. In this case we had a one-way ANOVA again. So under the single factor, variety is a single factor, and phosphorus content in wheat was the data, right? And variety is the factor. And then we had one column for P content, the other column for variety, right? So all these things, but when you do two-factor ANOVA, we need two columns for, so one column for one factor and another column for the another factor. Okay, and then the one column is for the data. Let us see this example. So data 1, I'm assuming that tooth growth data, which is the built-in data. Let me remove this and then see how the tooth growth data look like. Okay, let us see. This is the heading. I mean, I'm just doing the 5 data points or 6 data points. I'm just looking that. If you want to see the all data points, let me type that data 1. So that prints all the data points. You see that there are how many columns? 3 columns. One is the exact data length of the teeth length, right? This first column is for the factor supplement. There are how many types of supplement? There are 2 types of supplement. One is the vitamin C supplement and the other is the orange juice. You see that? So this has one factor as a supplement. The other factor is a dose. Under the supplement factor, there are 2 levels. One is the VC, the other is the OJ. Similarly, under the factor dose, there are 3 doses: 0.5 gram, 1 gram, and 2 gram. Right? You see that 0.5, 1 and 2 grams. See? Under the vitamin C. Under the orange juice, there are 0.5 and then 1 and then 2. So although this dose looks like a numeric, but we will be taking this as a category, like it is a different non-numeric data. But the data may be recorded like, let's see, how does the data types look like? You see that length is recorded as a numerical data. The supplement is recorded as a factor data or categorical data that has 2 levels. You see that? And the dose is taken as a numeric data. Okay? But what we want to see here is we want to see whether the tooth length is equal under the different supplement and also under the different doses, right? You see, if you administer 0.5 gram of the vitamin C, is that the length of the tooth is equal to the 1 gram of vitamin C or 2 gram of vitamin C or 0.5 gram of orange juice or 1 gram of orange juice? All those different combinations we will be checking whether the mean of those are equals or not. Okay, so first of all, what I want to do here is I need to have this as numerical. The main data must be numerical data, and then the 2 category or the factors must be categorical data. or the factor data, right? So what I need to do is I need to change this dose data into the numerical data of the dose into the factor data. How do I do that? This is the code how I do it, okay? So the data one dose equals to as dot factor data one dose. So the data one dose is changed to the factor data that way, okay? So if there are more than one non-factor data, what you can do is you can do the exactly same. What I'm trying to do here is I'm trying to change the supplement data into the factor, whatever data is this. It is already factor data, but just wanted to make sure and change all the factors as a factor data or a categorical data. Okay, I did that. Now if I run that code, string or the structure of data one is, you can see that the length is the number data, numeric data, and the supplement and the dose are the factor data. All right. So let us do you remember how did we do the one-way ANOVA? We did AOV and then length and then that wiggle sign and then supplement only, right? Or you did length and then wiggle sign and then dose only. But here, since you have a two-factor, what I do is, so this is just a name. I just did result of two-factor ANOVA. This is result of two-factor ANOVA equals to AOV. This first you need to write the data column, okay? Name of the data column is length and that wiggle sign and then supplement plus the dose, okay? Meaning you will be checking for both supplement and dose. So the data is data one. That's what we had, data one, okay? Now if you want to see which one is more significant or not, what we do is I am going to write the summary of that. Let me first run this and then write the summary of the result of two-factor ANOVA. What we got here is under the supplement, the F value is 14.02. The P value is less than alpha. What does that mean? That means under the supplement, there were two types of supplement. One is the vitamin C, and the other is the orange juice, right? So that is significant, meaning the average tooth growth or the tooth length under the vitamin C and the orange juice are different. That's what it is saying, okay? The average tooth length under the vitamin C and under the vitamin C and orange juice, with orange juice and vitamin C as supplement, are different. Let us see the dose. Under the dose, you have the F value is 82.81, which is the test statistic, and the P value is less than, very small number, right? So P value is less than alpha. That means this is also significant. Dose is also significant. What does that mean? That means under the dose, different doses, the average tooth length is different under the different doses. That's what it's saying, okay? So let us read what I wrote here. From the ANOVA table, we can conclude that both supplement and dose are statistically significant. Dose is the most significant because the p-value is a lot smaller than alpha there. So the dose is most significant factor variable. These results would lead us to believe that changing delivery method, supplement or dose of the supplement, will impact significantly the mean tooth length, which indicates that the level of supplement are associated with significant different tooth length. Also, the level of dose are associated with the significant different tooth length, okay? Now, we want to see if there is an interaction effect. What does that mean? That means we saw that the supplement is significant for the tooth length, right? Meaning that if you administer the with orange juice or vitamin C, then is that depends on the dose as well? Does the dose has any effect on the supplement for the tooth length or not? Okay. To do the interaction effect, what you do is you do exactly the same thing for this, but the one thing you do is plus supplement each to dose. This basically measures the interaction effect. So the data is data one. If I run this, what do I get? I got summary is, you see that The supplement is significant. We saw that already. Dose is significant. Also, the interaction is significant. So the supplement, so different supplement have effect on the tooth length, but that is also depending on the dose. Okay, so there is an interaction effect. So usually what we do is, if there is an interaction effect, because see, you see that for the interaction the p-value is less than alpha, right? What does this says? This says that if you supply with different supplement, if you give with vitamin C and orange juice, then the average will be different. What does that mean? This means that if you supply different dose, then their mean are different. But what does it says? What is the interaction significance says is, if you are giving a vitamin C, then you will be giving either dose 1 or 0.5 or 2, right? With those different doses under one supplement, you get different mean. Similarly, if you supply with orange juice, you will be supplying 1 gram or 2 gram or 0.5 gram, right? So under orange juice, there will be three different methods. It is also under each supplements, each of the two supplement method, you will be supplying 3 different doses, right? So the average with those 3 different doses under the same supplement method is also different. That's what it is saying, okay? If there is an interaction effect, we ignore the effect of the separate single effect of support and dose, and we just focus on the interaction effect, okay? Let us see what I wrote here. It can be seen that the two main effects, supplement and the dose, are significantly statistically significant, as well as their interaction, which indicates that the relationship between dose and tooth length depends on supplement method. If you supply from the vitamin C or if you supply from the orange juice, you will see the different length of the tooth with different dose. That's what it means. In such cases, we ignore the individual effect of independent factors. We ignore those two if this is significant, and we describe this one, okay? We describe the interaction effect. Now we will check the assumption of the two-way ANOVA. Okay, the first thing I want to do is I want to do the regular box plot. If I do the box plot, you see that? So under 0.5, these two mean are significant, right? Here the mean are significant. Here, this one is not very significant, right? So to see what they stands for, let me expand this and then I will say, look at this. So this is basically orange juice with 0.5 dose and vitamin C with 0.5 dose. You see that they are significantly different, right? Similarly here, orange juice and the vitamin C with 1 gram of the dose, right? They are significantly different. You see that there is one outlier, right, of the orange juice and vitamin C. So the supplement for the 2 gram of the dose looks like they are. So what we see here is when we do the normal box plot, you don't have to worry about this color, right? And X lab, Y lab color. So basically what we did is length, and then that's how, and supplement times the dose. That's how you plot both all together, supplement and dose box plot together for the length, okay? So you see that, and then now let me go over the interaction plot. The box plot indicates that there is an outlier in the vitamin C, right, of the 1 gram with the dose 1 gram. That's the outlier there. That's what it is talking about. Let us not worry about that for now. From the box plot, we somehow guess that orange juice has more effect on tooth growth than vitamin C. These are the vitamin C, these are the vitamin C, these are the orange juice, okay? So they have the more effect for the length of the tooth, or the tooth growth. From the box plot, we somehow guess that orange juice has more effect on the tooth growth than vitamin C when dose is 0.5 and 1. For a higher dose, it looks like they have the same effect because you see there, right? Same effect for the tooth growth. This can be seen clearly from the another interaction plot also. We will see that, okay? So let me run this interaction plot. What we did here is I did x dot factor equals to data 1 dose. So dose is under the x-axis as the factor. Dose is one factor placed under the x-axis, and trace factor is which is seen here. Okay, data 1 supplement. So supplement will be seen here with different colors or different types of graph there. So the response variable is the length. Data 1 length is the response variable. That's how we plot along the y-axis. And all those things are just the standard thing. So what we see here is for 0.5, vitamin C and orange juice has different effect on the truth length, right? For 1 dose 1 gram, it has the different, but for 2 gram, it is the same. That's what you can see from the interaction plot as well. So basically both of those plots are giving the same result, right? What we see from the plot is the effect on tooth growth is clear from the plot. X factor is the factor to be plotted on x-axis. Trace factor, the factor to be plotted as lines. And the response is a numeric variable giving the response that is plotted on y-axis. So the type is the type of the plot. Allowed values include P for point only. If there is P, it is point only. If there is L, it is for lines only. And then B is for both point and the line. You see that type is B. If you set that as L, it will give you line only with different color. Okay. Okay. Now the next thing is we need the homogeneity of the variance. That's the assumption, right? We haven't started as assumption. We just checked what we see from the box plot, right? Now we want to check the homogeneity of the variance of the supplement and the dose for length. Okay. I use the Bartlett's test. From the Bartlett's test, I got the p-value is greater than alpha, meaning the variance are the same. I use another alternative method, that is the Fligner test, gives you the p-value greater than alpha, which means the variance are equal. Now, but what is the what is the graphical techniques to do the homogeneity of variance? Is you do plot result.AOV3. How did that come from? This came from the ANOVA test, right? This name I used that for the homogeneity of the variance test graphically. What did I do is plot result.AOV3 and then 1. You see that? So let me pull this a little bit. Okay. If I do that, what do I see? I see that, you see that? So the dotted line and the red line almost the same, meaning the samples or the populations are have the homogeneous variance. Okay, they have the homogeneous variance. That's what it says. If it were like increasing or decreasing pattern, then we would think that they may not be homogeneous. The variance would be heterogeneous. But we already checked from the statistical test that the variance are homogeneous by using 2 different methods. Okay, only one method is enough to do that. Next one is normality. Okay, so what do I do for the normality? Do you remember that we use the Shapiro-Wilk test? Yes, we'll be doing that. So let's see. First of all, we need to define the residuals, and then we will plot the residuals. So AOB.residuals equals to residual, and then bracket object object equals to res.AOB3, which is the name of the output we had from the ANOVA, two-way ANOVA. Okay, that's what I am doing here. So when I do the residuals, and then if I do the Shapiro-Wilk test, I got the p-value is greater than alpha. So p-value greater than alpha means it is normal. The data is normally distributed. If you want to do the plot, okay, if you want to do the plot, you can see that the QQ plot shows that the data is normally distributed. So I did not remove any outlier because it is still with outlier. It is giving me the normal result, right? The normal population. Okay. Now the pairwise comparison. You see that what we see from the ANOVA is So this is, all of these are significant, right? Basically, this support and dose, the interaction effect of the support and dose is significant to the tooth growth, right? Now we want to see which pair is basically the significant and which pair is not significant. We remember that from one-way ANOVA, we're doing the 2K HSD. That's what I'm trying to do here. Look at this. So 2K HSD and then result.AOB and then comma which equals to supplement and is to dose. That's what it is giving. See, it will give you the hypothesis testing and the p-value for each of those possible pair. So the orange juice 1 gram versus orange juice 5.5, orange juice 1, vitamin C 1 gram, orange juice 0.5, orange juice 2 gram, orange juice 0.5, orange vitamin C 2 gram, and it is giving actually all possible combinations. And you see that so this is significant, this is not significant. What does that mean? That means if you compare vitamin C of 1 gram with the orange juice of 0.5 gram, they are not significantly different. They are almost the same. Similarly, this is not significant. What does that mean? That means orange juice of 2 gram and orange juice of 1 gram are not significantly different. And this one is not significantly different, and this one is not significantly different as well. So how do I say that? 11 out of the 15 computed comparisons were statistically significant, and the 4 of them are not statistically significant. So the next thing I want to do is, because you know this tooth growth data was nice format, it is already written in the column, but the example that we did in the slide, it doesn't have the nice format. So how do I create one column of, say, peak plasma calcium level, right? Plasma calcium concentration. The other column we need is treatment type, right? So T type. So T type. And the other column we need is the gender, right? And put this data here, and then the treatment type is like hormone, no hormone, hormone, no hormone, whatever there is, and then male, female, male, female. How do I write these things on the table? Because it is given in the nice grouped format, right? But how to write in the way that R can understand it? So let us look that. So what I will try to do is I will copy all the data like this in the R in one column, and in the second column, so what I do is I will do the treatment type, and then these are no hormone, no treatment, right? And the last two column are treatment. And then next, what I want to do is I want to name the first 5 as female, second 5 male, third 5 female, and fourth 5 male, that way. So how do I do that? Exactly the same idea you did for the one-way ANOVA. Okay, what I'm going to do here is, let us see that this is female with no treatment, right? So female with no treatment. Okay, so this code actually I posted in the Georgia view. So female with treatment, right? Female with treatment. You see that? So FT, MNT means male with no treatment, and MT means male with treatment. So this is the given data. Okay, I copied the columns of the given question. Now what I did is in the treatment type, what I'm going to do, under the treatment type, this is no treatment, treatment, no treatment, treatment, right? So I'll do repeat no treatment how many times? Length of FNT. So for all of these, each of these data, you assign no treatment, and repeat no treatment for length of MNT. So you see that MNT and FNT, male no treatment and female no treatment, are under the no treatment category. You see that? Similarly, repeat treatment with length of FT. How many data are there? You assign treatment for that. Similarly, treatment for the male data. Okay. Now here, gender is, so the first one is female. First first and the second are female. You see that? Repeat female for that many, and repeat male for MNT. See, for you see the order here, right? FNT, MNT, and then FT, MT. So I kept the same order there. You see that? And FT, FT, right? And here repeat female and then repeat male, because this is the male data, right? This is the female data. We are collecting them together, right? And similarly, the female for the treated one, and then male for the treated one, right? Male for the treated one. We collected that. Okay, let me run this. How does it look like? Let's see. I ran all those four names or the four data we had in the question. So the treatment type, I just discussed that under the gender. So what I'm trying to do is, what is the plasma content? These are the values of the plasma concentration, right? Plasma calcium concentration. So how it is ordered will be, first I put FNT, female not treated, female treated, male not treated, and male treated. That's how I'm going to put. Okay, so if I do that, then so this is the plasma CC. You will see that. Okay, let me run that one. Okay, now let us see whether it is following all the data. It is copying all the data from the graph, from the plot, right? 16.3, 20.4, and then 15.8, 9.5. All those data are basically, you can see here, right? You can see. But the one thing that different what I did here is I placed like this one first, and then I did this one after that. Okay, I collected a female altogether and then male after that. You can do whatever way you want to. Okay, you can do female and then you can do male. If you want to do that way, what you will do is, you will do treatment type is no treatment female, and then you can do treatment female. Okay, you can do treat and then FT. You can do that way, and do the same order here for the gender too, so that you will have those copied. Okay, now what I'm doing is I'm making a table like we had. Okay, so data one is in the tooth growth. Do you remember we had a 3 columns? So that's what I'm going to create. This is the main data, plasma calcium concentration. So treatment data is, treatment type is it is like hormone treatment, no hormone treatment, hormone treatment, no hormone, and that way. And this is male female data. Okay, let us do that. So this is just not going to the next. Okay, so look at that data. You see that? So plasma CC, all those are copied here, and treatment type, no treatment for 10 of those, and then treatment after that, and then for gender, male female. So if you look at, check each of those data points and the rows, you will see exactly what we have here. You see, you will see exactly the same thing, because you see that 16.3 no treatment female, 16.3 is no treatment female, right? 9.5 no treatment female. Next, treated female is 38.1. You see that? Oh, there is a problem. Okay, let me fix that issue, because it is 16.3, so it should be treated female. It should be treated female, right? So there is a male, so that's not male. That is not male. So what I'm going to do here is, so by the way, there was an error when I in the code that I posted in Georgia View. Just look at that. So there is a FNT and then MNT and then FT and then MT. You should have exactly the same order in the gender, and the plasma CC you should put exactly the same order. Otherwise you will get a different combination here. Okay, so first FNT and then MNT and then FT and then MT, and then this is the plasma CC. So let me run that. You see that, right? Now what I do is I will put that plasma CC and then the treatment type and then the gender in the same table as we have there. And then if I run that, you see that? Now you have, look at that. Let us compare this data and the columns that we got here. So the female 16.3, 20.4. So female no treatment, right? 16.3, 20.4, 12.4, 15.8, 9.5. See that? And then 15.3, they are the male, right? See, these are 15.3, 17.4, 10.9. You see that? All those are here, right? So all those are here basically. And similarly, the other female 38.1 are the treated female and then the treated male. So you got exactly the same way. So on the code that I put here, I have FT and then MNT. So please correct that. Okay, it should be first MNT and then FT. So you should follow exactly the same order there. All right, so that is the table we got. Now what I want to do is exactly the same way. So this is the data, main data, plasma CC. and wiggle. So I want to do the two of them only, like one by one, and then next I want to do the gender. Okay, I mean the interaction plot. I mean, you can do this directly. Okay, what do you see? What you see from here is the treatment type is significant. You see that? The treatment type is significant, meaning the hormone and the no hormone treatment has significant impact on the plasma calcium concentration, but the gender does not have significant impact on the plasma calcium concentration. Similarly, the treatment type, whatever the treatment type and the gender, the interaction is not significant. There is no interaction between the gender and the treatment type. That's what we got. Now let us see the since there is no interaction effect. Okay, so you just focus on the treatment type and the gender only. So what we say is, so the treatment type has significant impact in the plasma calcium concentration, and gender does not have significant impact on the plasma calcium concentration. Okay, so I'll do all those things that we did for the previous example. So what I'm trying to do here is I want to see that from the plot. I'm going to do in the basically I'm going to do this thing, the assumption check. So let us see this. What do you see here is, see, no treatment female and no treatment male. You see that the gender does not have much effect, right? And treatment female and treatment male, they don't have any effect, but there is a huge impact on the treatment versus no treatment female and treatment versus no treatment male. You see that? That's what we saw from the hypothesis testing as well, the ANOVA as well, right? So the treatment has significant impact, right? But gender and the there is no interaction, there is no gender impact on the plasma calcium concentration. So what I'm going to do is I'm going to do another type of the plot. You see that? So no treatment versus treatment, it is huge difference, right? But under the male and female, so there is not much different, right? With under male and female, under the category gender, there is not much different, but under the category treatment type, there is different. That's what we see here. Okay, now let us do the assumption. So the test of homogeneity, let us see what we get. So the p-value is greater than alpha, meaning the variance, population variance are equal. Okay, the next one, that was the Bartlett's test. Next one is Flinger test. So let us do the Flinger test. Not that one. Okay, let us do the Flinger test. So this is also significant, so we don't have to worry about the homogeneity of the variance. You see that? And then what we see on here is the normality. So what we do, by the way, let us check the homogeneity of the variance on the on here. Okay, so on the graph you see that the variance are equal. Okay, and how about the normality? So the normality is p-value, we got 0.3198, which is greater than alpha, so the data is normal. And if you want to see so let me see, where is the, let me do the QQ plot for the normality. Okay, so what I want to do is I want to do the QQ plot as well. So if you do the QQ plot, this is what you will get for the normality. Okay, if I do that, the data is almost normal. Now if you have to check the 2K HSD, I mean there is, right? But what we saw here is basically, if you go back, what you saw here is basically the treatment type is significant, right? So treatment type is significant means which pair is more significant under the treatment type. That's what we want to see, because there are two different treatment type, hormone and non-hormone, right? So there is only, if there are more than two, then the 2K test makes sense, because there will be more than one combination, right? Like treatment 1, treatment 2, treatment 2, treatment 3, like that. Since there are just like two treatment, there is only one pair. So let us run what it gives me, right? So what I'm trying to do here is I'm doing 2K HSD, and it will show all possible combination. But what you will see here is, so treatment female versus no treatment female is significant, right? Treatment male versus treatment female is significant. Treatment male versus treatment female is no treatment male and treatment female is significant, and then treatment male versus treatment female is also significant. So it shows that 4 out of 6 computed comparisons are statistically significant. So this is how you do the two-way ANOVA. All right.